Hello, welcome to this last talk. We are having a talk by Carlos Herdeiro from Aveiro, and uh, yeah, well, he's obviously eminent physicist working in black holes and compact objects, and he's also a very a long-time friend of Belém Group, as you know. It's a pleasure to have him, and it's also fitting to ask him to give a talk on spectrum and dynamics of bosonic stars and their hairy black holes. So go ahead.
Okay, so good morning, everyone. Thank you, Atsushi, for the kind words. I would normally start by thanking the organizers, but since I'm one of the organizers, that would be a bit strange. I'll only thank Luis Crispino and the people in the graduate program that actually did the work to put this very nice meeting together. So I'll talk about the spectrum and dynamics of bosonic stars and their hairy black holes. My goal is to briefly cover a number of interesting results in this class of models without lingering too much on details. And I should thank some of the previous speakers. You can't hear me well? Okay, but shall I do something like avoiding to move too much? But that would be challenging to keep it always in the same place. Okay, I'll try my best, but so I should thank some of the previous speakers for the overview and covering some of the topics related to bosonic stars, and also some hairy black holes, in particular Carolina. I think that this should make my talk rather simple, familiar, if not redundant. But it's always good to hear something you already know. I'll take that as a premise for this talk. So I'll start with the following remark. Our understanding of the most compact objects in the universe, in particular black holes, is based and to a large extent biased by our paradigmatic models. And the simplest paradigmatic model, for a good reason, that we start teaching our students is Einstein-Maxwell theory, that's electrovacuum. Now, this is a really nice model in which stationary and axisymmetric solutions are analytic. Actually, the model is integral. It can be cast as a nonlinear sigma model. There are many nice solution generating techniques. It also turns out that there are no solitons in the model, and this was covered in the lectures by Anna, also in some generalizations of the model. And these are, of course, localized, asymptotically flat, everywhere regular, horizonless lumps of energy, so not black holes. There are uniqueness theorems for black holes. So the most general asymptotically flat solution with a connected event horizon is the Kerr-Newman solution, regular on and outside the horizon. And it has no hair. This was actually mentioned in the lectures by Filippo. And its only macroscopic parameters are mass, angular momentum, and the gauge charges, electric and magnetic. These, though, are thought to be of little relevance in astrophysical setups as black hole charges, not, of course, in the environment. And finally, and most importantly, this model produces good phenomenology. I think it's fair to say that at the moment there's no tension between the so-called Kerr hypothesis and strong gravity data. And nothing of this really changes if instead of one Maxwell field, we have many. And this happens, for instance, in many supergravity theories. If we have two, for instance, we can cast the Maxwell field as a complex Maxwell field. But the dramatic change occurs if we add a mass term to this complex Maxwell field. Then we have a complex Procca field. And what happens here resembles very closely what also happens for Einstein-massive complex Klein-Gordon. So instead of having a vector, we have a scalar with a mass term. The downside here is physical because the mass term is an obstacle for the integrability structures, and even the simplest solutions in which the bosonic field is excited, the massive bosonic field, they are only known numerically. But the upside is physical. Now there's a very rich spectrum of solitons known as bosonic stars with a variety of new dynamics. And related to these solitons and also to the interesting phenomenon of superradiance that was already mentioned several times in this meeting, there are new hairy black holes and a related non-uniqueness. So one may ask how different is the phenomenology in these models as compared to the Kerr paradigm, and also if there are interesting conceptual applications of the model. So my talk is to advocate that these models provide a great testing ground for many ideas, even if not realized in nature, which is yet to be established. And today I would like to give you a brief overview about the spectrum, the dynamics, and some applications of these bosonic stars and hairy black holes that they help composing. So I'll start with the spectrum and dynamics of solitons and tell you a bit about these bosonic stars. From the gravity perspective, these bosonic stars appear in general relativity with simple and physically reasonable, namely obeying the most basic energy conditions, matter sources. And these are complex, massive scalar fields or vector fields, possibly with self-interactions, but not, it's not mandatory, but certainly with a master. Now, these two classical effective field theories I'm showing here are kind of singled out on a simplicity criterion, but it's by no means exhaustive. So we just have a complex massive scalar field minimally coupled to Einstein's gravity and a complex massive vector field minimally coupled to Einstein's gravity. The solitonic solutions here are called scalar boson stars, whereas here they're called vector boson stars, also known as Procas stars. Collectively, they are called bosonic stars. In these models, there is a new parameter, which is the Compton wavelength associated to these fields, which provides a new scale where you'd expect these things to become particularly relevant. So in the following, I'll call these two models reference models, but as I said, they are by no means exhaustive of this discussion that we can have here. One can also give bosonic stars a more microscopic perspective. They are often described as Bose-Einstein condensates of many ultralight particles in the same quantum state. Therefore, the classical action is much larger than h bar, and this justifies the classical description. The need for this ultralightness comes from the existence of a model-dependent maximal mass for the bosonic stars. So these stars exist, but there's a maximum mass, much like neutron stars. And here this is determined for the simplest models just by this parameter that appeared in the Lagrangian, the mass, if you'd like, of the fundamental boson that appears there. And the scaling goes as 1 over mu. If you put some units, it goes as 10 to the minus 19 for the maximal mass allowed, 10 to the minus 19 times the solar mass times the inverse of the fundamental boson's mass in giga-electron volt. There's a constant here that it's determined by numerics, typically of order unity. So if you'd like to have bosonic stars with masses in the astrophysical black hole range, which goes from about 1 to 10 to the 10 solar masses, then the fundamental bosonic particle must be ultralight with the scaling 10 to the minus 10 corresponding to here 1 and 10 to the minus 20 corresponding to here 10 to the 10 solar masses. So if you'd like these things to mimic to some extent the astrophysical black holes candidates, this is the range. And then if such hypothetical particles have feeble or no interactions with standard model constituents, probably interacting only via the Higgs portal, they are fuzzy dark matter and only detectable gravitationally. So this would be making a connection with the dark matter problem. Of course, from a high energy physics point of view, then there's the fundamental question how such light particles can emerge and how can they be stable. And there's various possibilities for this. A very popular one in the context of string theory has been the so-called axiverse, a landscape of these ultralight bosons coming from string compactifications. But I should say that there's much simpler models that I personally find very interesting that come from considering extensions of the standard model with, say, some copies of the electroweak sector, in which you also have massive bosons after the symmetry breaking, such like the Z and the W. But here you could have Zs and Ws with much lower masses. It's also sometimes called a hidden sector. Okay, so this idea that bosonic stars are sort of macroscopic quantum states also justifies a sort of an attempt to describe their spectrum using something very familiar, a hydrogen analogy, for which the quantum numbers are well known. This is a basic problem in quantum mechanics that we learn in the university as undergraduates. So the quantum numbers are NLM. This is the hydrogen atom without spin. And the frequency is uniquely determined by these quantum numbers here. And this combination is so-called the principal, N quantum number, capital N. So this is the probability density of the familiar orbitals from elementary quantum mechanics that you should probably be aware. So let us consider the spectrum of solutions for these bosonic stars from this perspective in our reference models. Now, the simplest solutions are spherical stars. In the spherical sector in hydrogen, so we have the so-called NS orbitals with this quantum number, combination of little NLM to be 1, 2, 3, 4, 5, and so on. And it's related to the number of radial nodes in the wave function given by this. That's little n. So here there's one radial node. For one s there's 0, and so on and so forth in the probability density. And you find this familiar shell-like structure for the orbitals. Now, similarly, for the scalar boson stars that are spherically symmetric, these can also be labeled by the number of radial nodes. So the fundamental state has no radial nodes, so there's going to be an excited state, n equals 1, n equals 2, n equals 3, and so on. And you can also see this shell-like structure very similarly to what you see in the familiar orbitals. So here, of course, we are talking about the energy density, whereas there we are talking about probability density. This is fully classical. But an interesting novelty actually occurs in the vector boson stars in the spherical sector, in which the number of nodes of the scalar part of the vector potential now actually starts necessarily with one node. And this was observed in the very first paper that described these Procas stars. Now, this raised the question if indeed this was the ground state, because there was this radial node. And I'll come back to this question very shortly. But before a little bit more of detail on the spherical boson stars with the smallest n, little n, which is little n equal to 0 in the scalar case and little n equals 1 in the vector case. Now, this can be labeled by their frequency. So when you calculate the solutions, you put the scalar field for the scalar boson stars or the vector field, having this harmonic time dependence. Note the similarity with stationary states in quantum mechanics. And there's a frequency. And you can label the solutions up to some extent with this frequency. And this frequency determines the mass of the solution. So these are very familiar diagrams in this sort of analysis. I guess you've seen them already in this conference. Here I'm showing for the fundamental spherical scalar boson stars, both the ADM mass, which is the red solid curve as a function of the frequency, and also the blue curve is the Noether charge. I will not discuss that. But here you see the same thing for the vector case, and there's a clear similarity, although these are a bit heavier. Now, people have looked at linearized radial perturbations, and I think Carolina mentioned this, of the coupled system, and shown that an unstable mode emerges here at precisely the maximum of the ADM mass. And this turned out to, lead to a commonly accepted conclusion that the right part of this branch here was stable. These bosonic stars were stable. In fact, this only showed they were stable against spherical dynamics, perturbatively. But stability actually turns out to be the case only for scalar stars, because for vector stars, there is non-spherical dynamics that actually makes them unstable. I'll come back to these non-spherical dynamics shortly, but before that, let me just tell you that in the unstable branch, there can be different outcomes of the dynamics, different fates, depending on the perturbation and also on the star, but they are unstable. Let me see a bit more on the spectrum of solutions. So it turns out that unlike black holes in electrovacuum, for which you know that Israel's theorem tells you that staticity implies sphericity, the spectrum of static boson stars is much richer. There are not only spherical solutions, but there's other solutions. Now, let us continue with the analogy with hydrogen. So, of course, you know about the p and the d orbitals and so on. And in particular, these correspond to L equals 1 and L equals 2. And here's the principal then quantum number. So there is a variety here of morphologies for the probability density. And there is something similar for the case of these bosonic stars. There are stars with a multipolar distribution as well. So here's the morphology of the angular distribution for the scalar model. And one could think about these solutions here in a simple way. These are complicated solutions, very complicated to construct, but there is a simple rationale. For that, you consider in flat spacetime the massive Klein-Gordon equation, flat spacetime. And there's a very well-known solution. You can put here a harmonic time dependence. Then there is a radial function that's given in terms of modified Bessel functions of second kind. And here these are real spherical harmonics in this case. So there are these solutions, and they depend on some quantum numbers. Turns out, though, that all of these solutions are irregular, are singular at the origin. But when you couple these to gravity, the nonlinearities of gravity regularize the singularity at the origin. So they're nonlinear self-gravitating configurations, versions, for the different choices of the spherical harmonics are these multipolar stars that I'm showing you here. So the last two numbers here in these trios correspond to the L and the M of this progenitor configuration in flat spacetime that you make then nonlinear by turning on gravity. So, for instance, these here are the monopolar stars, spherical. These are dipolar stars. They have two lumps. And here you have quadrupolar stars, these ones with a symmetry around the z-axis. So there's a clear hydrogen orbitals-like morphology. And like in hydrogen, you could expect that the energy is larger for larger quantum numbers. And this is illustrated here for this spherical, the monopolar, the dipolar, and the quadrupolar stars. So this is the curve for the ADM mass of the stars versus the frequency. And you can see that fixing the frequency, the star with higher, multipolar numbers then has a larger ADM mass. But when you try to do the same analysis in the case of the vector stars, the Procas stars, you find something different. So here are the masses along the space of solutions for the spherical case, so the monopolar ones, and that corresponds to this black dashed curve here. For the dipolar stars, which turn out to have this prolate morphology, and this corresponds to this blue solid line here, and the quadrupolar stars, which is the red solid line, and they have two lumps, at least in parts of the parameter space. And there are two remarkable features here. First, if you fix the frequency, the lowest energy configurations for frequencies which are expected to be in what we called before the stable branch, then the lowest energy configuration is not the spherical configuration. It's actually the prolate one, the dipolar one. And in fact, even in some part of the space, the quadrupolar stars have less energy than the monopolar stars. So it seems that the spherical state is not the one with the lowest energy. And this is sort of energetic evidence that they are not the fundamental state, indeed. Now, there's also morphological evidence because these prolate stars turn out to have no radial nodes. Whereas, as we've seen and discussed before, the spherical stars in the vector case, they start at one node. That was already a hint that they would not be the fundamental state. But of course, in order to show really if there's something stable, we should resort to dynamics. To see that, in fact, the stable state, the most robust dynamical state, corresponds to dipolar stars, let us consider what happens to a monopolar star, a spherical star, and evolve it numerically in fully nonlinear evolutions using the Einstein toolkit. So here I've picked up solution number 7, and let's see what happens. So these must be three-dimensional simulations, meaning that you are not imposing spherical symmetry. Earlier simulations that imposed spherical symmetry erroneously concluded that the stars were stable because the unstable modes are non-spherical. So these are, as I said, simulations using the Einstein toolkit. They were done, in this case, by Nicolas Sanchez Gual. And this was done using a machinery that we developed in a previous paper to study actually rotating stars. So on the left-hand side, what you are going to be seeing here is the imaginary part of the Proca potential. Whereas on the right-hand side, you're going to be seeing the energy density. So you start with a spherical star, and if it was stable, it would just stay there. But if there's some dynamics, it should evolve. And what you see is this. So I'll show it to you again. Around 2000 in these units that we are using for time, the changes become visible. The star ceases to be spherical and seems to develop a prolate morphology, and simultaneously it gets a kick in the Z direction. Well, first of all, this supports the hypothesis that they are decaying. The spherical stars are decaying to these dipolar prolate stars. And this kick that you're observing here seems to be generic in these decays. And this decay from spherical to prolate solutions, with the first being even and the second being odd parity solutions in terms of the vector field, turns on a momentum term in the metric that seems to trigger this kick. Physically, there is momentum, of course, being emitted in the opposite direction, and this seems to be carried mostly by some remnant Proca field. By contrast, if you actually start with the prolate stars in what we would expect to be the stable branch, they show no dynamics. So here there's an example. These evolutions run to about 20,000 in these units. On the left, again, you see this imaginary part of the Proca potential. Sometimes you see phase dynamics. You're just catching it at a time slice where the phase looks the other way. But there's no real dynamics, as you can see here in the energy density. They remain prolate, and they seem to be robust, at least in these fairly long timescales. But then, okay, fine, that's kind of interesting, but could you actually form these things? Of course, if you have some object that you'd like to play a role in any physical context, you must address the question, how does it come about? And I mean, first of all, there's a long story here. Cosmologically, you have to justify how this massive vector or scalar fields would appear, and that's a separate discussion. But if they exist, then they are prone to gravitational collapse. But the most generic situation is you'd start with a sort of dilute spherical cloud of the corresponding massive bosonic field. What kind of object would you form? So here, if one starts with a spherical cloud of this vector bosonic field and does not impose spherical symmetry, does then one form a prolate star, or you kind of form a transient spherical star? Well, indeed, imposing no symmetries, one clearly observes that the collapse leads to the cloud breaking the spherical symmetry, and hints, although in these simulations you never really prove anything, that the final equilibrium state has a dipolar structure. So it seems that this is the state that's preferred for these objects dynamically, and they are the ground state. Okay, so enough about the static stars. Let us continue our discussion about the spectrum, but now considering rotating solutions. So here, a kind of a bit of a looser analogy with hydrogen orbitals would be that these are a sort of superposition of many orbitals with the same m, the azimuthal quantum number, but different L's, rather than just a pure orbital. Now, the simplest rotating solutions, they have little m equals 1, and n number of radial nodes of the appropriate function equal to 0. It turns out, and this was not obvious to anticipate, that in the scalar case, such stars have a toroidal morphology, not really topology of the spacetime. Spacetime is topologically trivial. It's the morphology of the energy distribution. It's toroidal, whereas in the vector case, it is spheroidal, like the Earth, the rotating Earth. Other rotating stars, more excited, also exist. So, for instance, we could consider a star. This is a Broca star, an example of a Broca star with little m equals 1 and little n also equals 1. So here there's going to be a node which corresponds to a vanishing of the energy density along the equatorial plane. And this gives a Saturn-like morphology to this Broca star. These higher excited states are typically thought to be dynamically unstable. And in fact, I'll show you for this particular case, this is indeed unstable in a couple of slides. But even the most fundamental scalar rotating boson stars turned out, and this was again not obvious, to be dynamically unstable in our reference model. So they were found to develop a non-axisymmetric instability, and this occurred at a moderately long time scale of the order of 1,000 light crossing times. So this is not too long. This can be seen again in this visualization. This is again a numerical simulation. This one was done by Miguel Zilhão. We're using again the infrastructure that has been developed for bosonic fields, just to show you that with these fields it's possible to do a lot of dynamics. And what you see on the left here is the color code denotes the scalar field amplitude. You're looking at this toroidal star from above. And at some point, you see that there's a non-axisymmetric instability that develops, and essentially all of the scalar field vanishes. This can be seen on this right plot. The scalar field is this red dashed curve. It kind of goes essentially to 0. And at the same time, one can detect the emergence of an apparent horizon. And this is the mass related to the apparent horizon. So the mass essentially falls into a black hole. This is a Kerr black hole, although it hasn't got fully to equilibrium, but it appears to be very compatible with essentially a Kerr black hole. So these stars collapse into a black hole fairly quickly. But on the other hand, this instability is not seen for the cousin Proca model. And this could be deduced for, again, numerical evolutions with timescales about 10 times longer than the ones for the scalar case. And as an illustration, here on the left panel, one starts with a spinning Proca star with a strong perturbation, such that you see, I mean, although this is a bit heuristic, that it looks a bit deformed as compared to the prolate image that I showed you before. And on the right panel, one actually starts with an excited star, precisely the one I told you before that I was showing it would be unstable, the one with n equals 1, m equals 1, the Proca star, where there was this morphology Saturn-like for the energy density. And what is important is that in both cases, you don't see collapse into a black hole. You see that it seems to approach a spheroidal configuration. This can be tested by some more quantitative indicators, of course, which retains the angular momentum. So it doesn't lose. So it's not, decaying to something that's static. So the bottom line that I wanted to tell you about is that the spinning Proca stars are dynamically more robust, at least in the simple models, although adding self-interactions may have an important impact. I will not go into this story, which is a very nice and recent story that has developed how these things change if you add self-interactions, but I'll be glad to talk to you more at the end if you'd like. So to summarize, although these scalar and vector stars, they do have a clear parallelism in terms of the space of solutions with mild differences, dynamically a surprisingly different picture emerges with the solutions that are selected by dynamics being quite distinct. So in the scalar model, it is these monopolar solutions, static, that seem to be the dynamically robust ones, whereas in the vector case, we have that the static solutions are dipolar, and the rotating solutions, these spheroidal solutions, seem to be robust, at least moderately long time scales. Perturbation theory is something that has not been addressed for the rotating solutions. It's quite challenging, but there's work being attempted in this direction. That would be a very nice thing to complement these numerical experiments that people have been doing. Again, self-interactions can have a very non-trivial effect. That was written here. If you have the ability to interpolate or to extrapolate half of the text to the full text, perhaps you can conclude that. Not very easy, though, at least for me, but anyway. So what was written there is that self-interactions can indeed change this. It's another story that I cannot describe today. Let me just conclude this discussion about the bosonic stars by saying that what I've told you so far is for models with a single complex field. But of course, people are very imaginative, and so they've started considering more than one complex field, so more than one scalar field or more than one vector field. And there's more structure in that case, and the building blocks are kind of the same as we've discussed before, the single field solutions, but constructing appropriate superpositions leads to sorts of new structures like these L boson stars. So this is an example of a space of solutions for three complex scalar fields, which contains a special case of some of the solutions we've described before. There's this new spherical so-called L boson stars, and the whole study of dynamics and phenomenology for this is a big field in itself. Okay, so let me now move on to the spectrum and dynamics of the hairy black holes associated to these solitonic objects that our models allow, because there's a very important connection. So this very same class of models that I've been discussing, I call the reference models, besides having these bosonic stars, they accommodate some new black holes. They also accommodate Kerr because, vacuum GR is a consistent truncation, so that's fine. But they also accommodate some new called hairy black holes that can be seen as a horizon inside of a spinning star. This can only be done for spinning stars, and the simplest case will be for little m equals 1 and n equals 0. There's gonna be other, hairy black holes, but here I'll focus on these, which are the simplest hairy black holes within this family of models. So these Kerr black holes that emerge as solutions of the vacuum theory, they actually have the property of being prone to superradiant instabilities of such massive vector fields. And this is particularly efficient when the Compton wavelength associated to this is of the order of the Schwarzschild radius of the black hole. So in that case, there's some fairly sharp and fast dynamics that could extract some rotational energy from the black hole and pass it on to the complex bosonic field, creating a cloud or a hair around the black hole. And the process ends when there's a sort of synchronization condition occurring, which I'll mention. I believe that Carolina has already discussed this, but it's okay. I'll discuss it again. Um, and of course, the process is a kind of a process that goes in as a cascade. There will be then further superradiant modes, but at least for very large black holes, the further superradiant modes can be very long-lived, even cosmological timescales, such that the first, set of clouds could, be sufficiently long-lived to play a role in astrophysical process. Okay, so then these new dynamically emerging black holes from superradiance could be long-lived. I'll give you more details about all of this. And in some parts of the parameter space, they can have some very different phenomenology, namely new gravitational wave features in MRIs. And I believe Manuel mentioned this in his talk. So there's an interesting, at least in principle and theoretically, analysis about phenomenology of this family of solutions, which continuously connects to Kerr and continuously connects to our boson stars. So without too many details, again, these solutions are typically found numerically. A possible ansatz, not unique, to find this is this one here that has been used in a number of papers. So there's a metric written for a spinning black hole with a horizon at r equals rh. It's spinning. This function here at the horizon is the angular velocity of the horizon. So then the theta dependence doesn't change, the w, at the horizon. And again, for the scalar field, we have this harmonic time dependence introducing the frequency and the azimuthal harmonic index, and there is a profile function. The fundamental solutions have little m equals 1, and it's fundamental for the solutions to exist that the angular velocity of the horizon and the phase angular velocity of the scalar field or the vector field, they match. That's what's called synchronization condition. The intuitive idea is that there is a continuum of hairy black holes that interpolate between Kerr black holes and these rotating boson stars as a kind of nonlinear superposition. So this suggests that we can look at the two limiting cases for insight. Near the Kerr black hole, the scalar field is small, and we can use a test field approximation around Kerr. Near the rotating boson star limit, the black hole is small, and we can think about a test particle approximation to describe the black hole. So these both can lead to insights on the solutions and their dynamics. So let me tell you something about this, first looking at the Kerr limit. And this is a very old but beautiful story. So we consider a test scalar field around Kerr, and we can ask, how can the scalar field be in equilibrium with the horizon? So if you think about Schwarzschild if you put a scalar field there, it is absorbed. It can be faster or slower, depending, but there's always some absorption. Well, this synchronization condition actually means that the scalar field mode is at the threshold of superradiance. And if you analyze it from a slightly different but related perspective, it means that there's zero flux through the horizon. Some more details. This is fairly simple. You do a linear analysis of the Klein-Gordon equation on Kerr. So this is again our massive Klein-Gordon equation. On Kerr, you can do this decomposition, that's well known. And you have this spheroidal harmonic, some radial functions. And for the radial functions, you get the Tucholsky equation. In fact, for a scalar field, it was derived earlier than Tucholsky. And so you can think about this as even a kind of one-dimensional quantum mechanical problem, except that the Hamiltonian is non-Hermitian, because in general, there is absorption. And therefore, the frequencies that come when you try to compute the normal modes are complex. They have an imaginary part. So one does not obtain in general quasi-bound states. Bound states would mean just a real frequency, but one obtains quasi-bound states with an imaginary part for the frequency. And it turns out that the sign of this imaginary part depends on the relation between this real part and the critical frequency, which is precisely what we've seen before as our synchronization condition. So if the imaginary part, if the real part of the frequency is larger than the critical frequency, and this is the only possibility for positive frequency modes for Schwarzschild, the imaginary part is negative. And that means that there's decay. And that's what happens for a Schwarzschild black hole. The field is slowly decaying. This field is massive, so there is a potential barrier at infinity, so it's slowly decaying into the black hole, slowly or fast, depending on the parameters. If the real part of the frequency, though, is smaller than the critical frequency, which is something possible when you have rotation, because then the angular velocity of the horizon is non-zero, then this is the superradiant regime, where there's growth. There's energy extraction, which, because of the potential barrier, is recurrent, so it's an instability, and therefore you actually have the growth of the mode. And it's been a question for a long time, what was the end point of this instability? But by continuity, it's obvious that if you have exactly the frequency equal to the critical frequency, in this case is the whole frequency, because the imaginary part vanishes, you have a true bound state. And it's really, really beautiful, because if you do this for an extremal Kerr black hole, you actually get the same radial equation that you get for hydrogen. It's a confluent hypergeometric equation, a Whittaker equation. It's really the same thing, and it's really beautiful. So it's really kind of an atom in the sky, if you'd like. So this, of course, seems highly fine-tuned, therefore unstable, that you get exactly this frequency. But then, and Carolina spoiled my metronomes, but I'll give them to you again. It's fine. I really appreciate that people use it. So if you are unaware about dynamical synchronization, so looking, for instance, at this system, I'm not sure if you can hear it. Well, it's synchronized. So it's a set of pendulums or metronomes in phase. You may think this is highly fine-tuned, how the guy managed to do this. But it's actually not true. With arbitrary initial conditions, if the right couplings are present, in this case, the right coupling is just to put your metronomes moving on a platform, and this communication of energy can be endowed by these cans that you put in the bases. And then you start with some arbitrary initial conditions, and quite fast, actually, they synchronize. Synchronization, here it's in a mechanical system. It's what, I mean, there's a whole landscape of biological and physical phenomena where this occurs. And for instance, fireflies, they tend to synchronize. There's a lot of animals that tend to synchronize. So there's a sort of a whole, discussion in biology about synchronization of living systems and also in physical systems. The fact that the moon is always showing the same face towards the Earth is an example of tidal locking, which is dynamical synchronization. In fact, this happens for essentially all the moons of all the planets in the solar system and probably beyond because of tidal effects. But in our case, without going too much into this story, which is a beautiful story per se, this sync state is in which a hairy black hole is formed via superradiance. And evidence comes from fully nonlinear evolutions that at the end are addressing what's the end point of the superradiant instability of black holes. And these were done first successfully by East and Pretorius already 10 years, almost 10 years ago, 8 years ago now, in the Proca model. They chose the Proca model because the leading superradiant instability is faster. And one of the problems here is that this takes a long time, which numerically is very challenging. So what you see here is that there's for several parameters, the growth of the mass in the cloud or the angular momentum in the cloud, starting from a little seed. And here what you see is the spin down of the black hole. And this is essentially the phase angular velocity of the leading superradiant mode. So you see spins down until it matches the right frequency. And then we, looking at their data, were able to identify that these endpoints seem to match very well some of these black holes with synchronized hair that were obtained as equilibrium solutions. Now, there's a few things that should be said. You cannot extract as much energy as you'd like. There are limits. First of all, there was a limit that Hawking actually proposed many years ago for energy extraction via the Penrose processor superradiance of 29%. This is easy to understand. But what seems to be the case in these simulations is you don't extract more than 9%. That was the result of these simulations. But of course, they didn't explore fully the parameter space. So we came up with an argument that given the properties observed in these simulations, in principle, energy extraction should be bounded by about 10%. So you cannot create an extremely hairy black hole. Of course, I mean, 10% of energy, if you think about, say, something like M87 star, so 6 billion solar masses, 10% of that is a lot of energy. That's a lot of energy. If it deforms a lot the space-time, that's another matter. It depends on how the energy is distributed, but it's a lot of energy. So there is dynamical evidence for this. Now, for the scalar case, similar evolutions could not be done, but what I would like to report here are some dynamical results that have been obtained, not involving the superradiant instability of Kerr, but the black holes with synchronized hair themselves. And this again used the infrastructure of being able to solve and evolve the Einstein-Klein-Gordon equations in this case in a computational infrastructure like the Einstein toolkit. So we've put here one of these hairy black holes. What you see here is essentially just a scalar field. There's a horizon at the center, which is kind of small here. And here you are looking at some phase dynamics again. So this is a black hole that's hairy, but not too hairy. So 25% of the energy is in the hair, 75% of the energy is in the horizon. You can split these two quantities very clearly using Kolmar integrals. It's very clear. There's no doubts about that. So you can have a clear amount of hairiness, if you like, via this measure, but there's various measures you could consider. Anyway, so the outcome here is rather boring. Basically, what you see is that you don't see anything. So if you've evolved these sort of not very hairy black holes, nothing happens. This has not been pushed to too high, times. I'm happy to report there was a paper today, for the ones of you that have seen it, about instabilities by our group of these hairy black holes in the very hairy regime that I'll talk about later. I learned also that Carlos Palenzuela and the group his group in Spain was doing these simulations, and they agree with this, that Black holes with not too much hair, they show no dynamical instabilities. So that seems to be the case, although some details are still to be filled in, which is interesting. But I would like now to tell you about the other limit, the limit where you have really a lot of hair. It's a tiny black hole with this boson star environment around that's dominating the gravitational potential. And can we have then stable configurations? And the first question is this equilibrium between a small black hole and a big boson star stable? Well, the black hole and the boson star turn out to form an unstable equilibrium. It's kind of funny because we've been thinking about this for 10 years, and then when you kind of come up to the right sort of way to look at it, it's kind of obvious. But, things take a while. And this can be understood from a geodesic approximation. As I've said, now we could consider the black hole as a kind of a test particle almost in this very hairy limit in the environment of this big boson star. Um, and you could think if this, in geodesic approximation, if you put a point at the center of this boson star, if it would be stable or not. But you can also do even something simpler, which is you can do a Newtonian toy model. And we've discussed it already in this meeting, and this is quite insightful. So the boson star is a kind of a mass torus. It's thick, but I'll do a simpler toy model. I'll put a thin, actually infinitely thin, ring of matter on the equatorial plane, xy plane. This is in Newtonian mechanics. There's a radius r, constant mass density. And then you can imagine what happens if I put a particle there. Well, the gravitational potential in the Newtonian approximation is something very simple to compute, an exercise for undergraduate students. And then you can plot it on the equatorial plane, and you see what you would expect, something like this, where this point is where the ring sits. I've put here capital R to be one. And then if you look at what would be the potential felt by the particle here at the origin, then, well, it's an inverse harmonic oscillator, so it's unstable. It just wants to fall. If you push it a little bit, it will go towards the ring. So under small perturbations, that's what happens. It's stable in the z direction, by the way, but not in the radial direction. Then this seems to match very well what we are seeing when we've performed the evolutions with these very hairy black holes that were reported today in this paper. And this is an example where the black hole has only about 11% of the mass of the space-time, so almost 88%, more than 88% of the mass is in the cloud here. And the cloud or the hair, sometimes I use one, sometimes I use one. And what happens? There are little numerical perturbations, obviously, and after a while, the thing starts to come out. But it doesn't go radially like in the Newtonian model because there's frame drag. The star is rotating, so it kind of creates a spiraling out motion. And when the black hole actually reaches the region of high scalar energy density, it disrupts the star completely. And most of the scalar field, essentially, not all, but most of the scalar field is again absorbed by the horizon, and the horizon mass increases. So what seems to be happening is that these very hairy black holes are unstable, and they have this sort of dynamics. But what you are getting is a kind of a Kerr black hole, perhaps with a cloud of less energy around. But this Kerr black hole is again unstable against superradius. So in a sense, it's a migration towards the region of black holes with not so much hair within this model. All right, so as a brief summary of the dynamics of black holes with this sink hair, the simplest model here, let me say that on the one hand, near the Kerr limit, Kerr is unstable against superradiance, forming these hairy black holes as transient states. The hairy black holes formed from these superradiance, which have up to about 10% of the energy in hair, could be sufficiently long-lived to be astrophysically players. more interesting in supermassive black holes where these timescales are longer. And super radiance efficiency, I didn't talk too much about this, but selects a preferable scale. So if you would have, say, an ultralight boson with a mass of 10 to the minus 19 electron volts, then this selects black holes like M87 star for creating hair, because the resonance is very important. As you go away from the sweet spot in which the Compton wavelength matches the Schwarzschild radius, the timescales for superradiance go up very fast. So this goes into something I consider very interesting, which is the universality of the Kerr hypothesis, which is we have evidence for black holes in this range of scales. Are they all really Kerr black holes? Could it be that in some intervals they are, some intervals they deviate in some way? Then when we look at the rotating boson star limit, then the spinning boson stars are afflicted by a non-axisymmetric instability, as we've seen. Then hairy black holes where the scalar environment is gravitationally dominant, they are in an unstable equilibrium. And this development seems to lead to a sort of migration to an approximately Kerr black hole, and that takes us back there. So there's a complicated dynamics, but what seems to be the case is that there could be a possibility for some deviations from the Kerr model somewhere in the spectrum of black holes. Now, one interesting question deviating from the reference models is, how about if you put the self-interacting potential there? The question is very interesting because it was shown that self-interactions can mitigate or even completely quench the instability of spinning boson stars, this non-axisymmetric mode. And this can be sort of understood by the morphology as well, because as you increase the self-interactions, they become less and less toroidal and start to become more and more spheroidal. However, looking at models of spinning boson stars in these with self-interactions in the geodesic approximation, one always concludes that the origin is an unstable equilibrium for geodesics. So there seems to be little hope that this could solve the mechanical instability that we are seeing when we put a black hole at the center of a boson star. Perhaps a more interesting case could be the Proca model, because, well, first of all, as we've discussed, the Proca stars, to start with, they are spheroidal rather than toroidal. And this non-axisymmetric instability that we've seen here, it's not shown there, doesn't appear there. So then if we also look at the behavior of geodesics here, there are, at least for co-rotating motions, the origin is an equilibrium point, which is stable. But the counter-rotating motions behave differently. So there's an interesting question about these very hairy black holes with Broca hair, if the story is going to be similar or different. Okay, so to wrap up a little bit about this overview of synchronization as a generic mechanism to endow spinning black holes with hair, I would like to make this point. It is a very generic mechanism. People have constructed, as long as you have a spinning object, you can put hair around it of such a bosonic field or classes of bosonic fields using this synchronization condition. So this was the simplest model. With scalar or Proca hair, you can add self-interactions. You can go to other dimensions. You can go to other asymptotics. In fact, there was a first example by Diaz, Santos, and Horowitz back in ADS before our example in asymptotically flat. And so you can go to other asymptotics. You can add electric and magnetic charges. You can have non-canonical kinetic terms, non-minimal couplings going beyond GR. You can have excited states as well, putting black holes inside of excited boson stars. You can put multipolar scalar hair. You can use this to build equilibrium configurations of two black holes, which are everywhere regular on and outside the horizon, which are asymptotically flat, a bit like Majumdar Papapetrou, but without gauge charges. because the scalar interaction can become repulsive in some circumstances, and we'll see that in a minute. And there is, you might have imagined, a purely charged version of this whole story using a resonance condition rather than a synchronization condition. So you can endow, also rise the Nordstrom black holes with this type of hair, but there's a big subtlety there, which the hair needs to be self-interacting. A mass term is not enough, and I can discuss that further with you if you'd like. So, and then many people have studied many theoretical phenomenological aspects of this. It's a playground, I would say. I would like to end just by giving you some applications. How long do I have, Atsushi? Yes, I think so. Even less, I would expect. So let me briefly present some applications of the model. And the first one that I found really interesting and was a little bit discussed, I believe, in my public talk is mimicking gravitational wave data. So some of these boson stars seem to be dynamically stable. So you could do interesting dynamics with them. We've seen that the spinning Procus stars seem to be dynamically robust, so they can be collided. You could put them in binaries and then start to extract gravitational waveforms. This is easier said than done. There's a lot of technicalities to make this machine work, but under the leadership of Nicolas Sanchez Gual, a first catalog of waveforms from collisions of spinning boson stars was constructed, which at the moment has about, well, it was written here, I believe, about 750 waveforms. And then you can vary things. So for instance, this is waveforms. So here one is sweeping the parameter space for initial data, so the stars you're colliding, and seeing how the waveform changes, okay? So there's a waveform. For each collision, there's a waveform. And you're just changing here, say, the frequency of the stars, and these are for equal mass. So these are for an equal mass, considering different frequencies, some examples. And here you excite higher mode. So here you're exciting, so this is the fundamental quadrupolar mode. So here you're exciting a higher mode as well in these waveforms. The point is you build a library of, putative responsibles for transients that we are observing, and therefore you could compare it with data. And because of the peculiarities of what one is doing here, one cannot at the moment compare with many events where you have a clear in spiral. And therefore you have a signal like, say, GW150914 or the one 15250114 that I've shown you before in my public lecture. But there's some specific events that you do not see the in spiral. So, and for some particular reasons, they are very massive typically, like GW190521. And so you could compare with that. So that was what was done in this PRL that was published back in 2021, led by Juan Calderon Bustillo, which also, he's an expert on statistical preference and Bayesian analysis. He actually participated in the Bayesian analysis for this event for LIGO. And then he repeated it for the models that we were generating with these Procus stars. And here the point is that it is competitive. For this particular event, it was competitive. So when you look at this log Bayesian factor, so I won't go into too many details here. There's different priors that you can use for this, but there's some slight statistical preference depending on the prior, even for the collision of head-on equal mass protostars or head-on unequal mass protostars as compared to the quasi-circular binary black hole model. The larger this number is, the higher the statistical preference. It's not very significant. I mean, it would be a statistical preference of a factor of 2 to 30, but it shows the genus. It shows that you could explain the same data with a different model. And this is a proof of concept of how you would go also from a different fundamental model into phenomenology and extracting physical conclusions. So about extracting the physical conclusions, the interesting thing is that then you could identify, because you're identifying what's the best fit modeling in terms of these Procastar waveforms to the data, you could start extracting what is, under some assumptions, the mass of the fundamental particle that's creating these Procastars, and that's explaining the data. And you can get to a prediction for this particle, a particle of about 8 times 10 to the minus 13 electron volts. Again, I think this is a proof of concept, but it shows something really nice. I mean, if then in population studies such a model would actually prevail, you would be detecting with gravitational waves a new particle. And that makes them particle detectors, which is a really cool idea. It dates back to superradiance studies, but it's really a cool idea. A different application is to show how some boson stars can actually exhibit an effective shadow without a horizon and thus mimic EHT data. So this was nicely illustrated in this paper here. I'm not an author of this paper. It was led by Hector Olivares and includes Luciano Razzola, for instance. And this is using GRMHD simulations on the background of the usual black holes of general relativity, as well as for some boson star backgrounds. None of these boson stars that are used have light rings, yet they notice that some of these stars could produce an effective shadow, like this model A here. Others didn't. And both these models, the models that could actually show this effective shadow, they noticed that there was a property that, the circular motion of matter, time-like circular orbits, they have a frequency that in those models attained a maximum at some radial distance from the origin. They claimed that this geodesic structure would mitigate the magnetorotational instability that actually is responsible for the loss of angular momentum and the inflow of matter towards the center. So what that means is that matter doesn't fall. It creates a sort of a void, and therefore you don't have emission from the center for that reason alone, which is interesting. That's certainly something that, well, doesn't happen in Keplerian dynamics. If you put a point particle and you analyze, just the Keplerian orbits, the frequency goes up all the way until the center. But because of the mass distribution of these boson stars, this happens in some models. Unfortunately, the models that actually show this property, they are unstable in this case. So this is done as a sort of test GRMHD. So you do not evolve the background. It's just you're evolving the plasma. But recent developments, which I'm not going to show, have looked at other models of boson stars where you can actually have a similar feature for stable solutions. It seems to be fine-tuned, but it shows how even in some sort of realistic analysis, state-of-the-art, computational tools to analyze the behavior of matter around black holes, you could have templates from an exotic object that could mimic to some extent what we are seeing from black holes. And as my final observation, I would like to tell you that there could be also some novel phenomenological features, which can be easily used to eliminate models, or it could be fitting some unusual, information. So if you remember in my public presentation, if you were around, there was this Tarzan, screaming. So maybe this would be a Tarzan scream. And so recently with a student in Valencia, Gabriele Paloni, who led these simulations, he was colliding Broca stars, and he was looking at the effect of the phase. It's very interesting because when we think about black holes, they're very simple, right? So that mass, angular momentum, even then, when you want to do collisions, the two-body problem, you can orient the spin in different ways, and that complicates things quite a lot. But that's it. And in boson stars, you have this phase. The phase for a single star is not something very important because at the level of the energy density and the energy momentum density, it doesn't matter. But if you have two stars, the relative phase is important. In particular, if there are phase differences of pi, meaning that the scalar field is changing sign from one to the other, the scalar interaction becomes repulsive. So in collisions where this happens, the scalar interaction starts to dominate the dynamics as they become closer. And that makes them bounce back. So they approach, but then they bounce back. Now, the scalar interaction, it's a Yukawa type of interaction. It has a mass term. So it only dominates at small distances. So as you go back outside, it becomes attractive again. So it goes in. And so when you look then at waveforms, what happens is that you don't have, your usual kind of increasing of amplitude in frequency. You have several bursts. So this would be a phenomenological feature very different for this type of objects, which would be very hard to, explain with a black hole model. Of course, we haven't seen this, maybe we'll never see, but shows how this model gives you different things. Okay, and I'll end here. So I would like to repeat that for these reference models that I've considered, they offer numerous possibilities, including a variety of solitonic objects, also of black holes. Of course, the possible realization of these objects in nature is another issue, but their connection with models of ultralight dark matter in appropriate mass ranges helps to justify to some extent, albeit in my personal view, it's not strictly necessary, this sort of theoretical excursions that we are doing here. At the end, into a deeper understanding of general relativity beyond the electrovac. With that, I'll end. Thank you so much.
Thank you, Carlos, for a very nice talk, covering lots of ground, but still reporting very recent results.
Even today, a paper.
Yeah. Any questions?
Which, by the way, was not an accident. We put it on purpose today.
Thank you very much for your presentation, Professor. It was really interesting. And I was wondering, hello, are you listening? I was wondering about, it's because, well, boson stars, uh, either scalar or vectorial, with vectorial fields, they are not only motivated to be black hole mimickers, but also as they can be they also could be constituted of dark matter, for instance. And I was wondering which kind of boson star, Broca star or a boson star, is most well motivated to be constituted of dark matter, and also be used, as you say, to analyze not only the gravitational features, but also as background to study and detect particles that could be represent dark matter, for instance.
Thank you very much. That's a very, very good question. And I do not have a complete answer. And I'm not saying it's a very good question because I do not know the answer, which is typically the answer when we do not know the answer. We say that it's a very good question. But so it goes a little bit beyond my analysis. That's the point I would like to make to you. So here we take these effective actions at face value and we analyze their strong gravity consequences. The question you're asking goes a little bit beyond. It goes to the embedding of these models into high energy physics, and then some cosmological dynamics that could lead to the production of these particles in the early universe and to their abundance, so that they could be indeed, part of the budget of dark matter and how much they can be. So about the first part, which is the embedding in high energy physics, it seems from the many discussions and works that I've been trying to do with some high energy physics colleagues, the Broca model offers some advantages. Why? Because if you just repeat what nature has given us, which is the electroweak sector, in which we actually start with gauge invariance, but we have a symmetry breaking via Higgs mechanism. We do create, particles like the W and the Z, and the W is exactly a complex vector field, which is massive. You just need to find a way to repeat the story, but such that the scales involved are very different. Because if you remember, the mass of the W and the Z are certainly not in the ultralight regime. And this appears associated to gauge symmetries. The scalar models typically appear associated to global symmetries rather than gauge. And gauge symmetries are typically, the strong anchor in our high energy physics model. So because of that, we've been trying also to look at the possibility of studying cosmological abundance of some of these ultralight bosons in the early universe. And it is possible to some extent to get them to be a contribution to the dark matter budget, even the whole of the dark matter in some cases. But this is something that's ongoing work. I cannot give you a final answer about that. What I think is that your question is very much related to something that goes a bit beyond. So we started with this game as GR people. You postulate something, you see what happens, which is fair enough. But then if you want to take it to a more realistic, level, then you have to consider other things, not only the embedding in high energy physics, but also its universe, its kind of how it develops in the history of the universe, such that we could get to a point where there could be these particles that could collapse to form black holes or other compact objects. So that's the answer I can give you at the moment.
Thank you very much,
Sure.
Professor.
Yeah, I think we have time for another Ooh. Okay, two questions. Yeah. Filippo? Yeah.
Thank you very much. It was a beautiful talk. So at some point you said that you have some argument to explain why the bound related to the energy extraction of the Perron's process should be lower. Can you comment a bit more about your argument for
Sure,
that?
sure,
Thank you.
So the argument goes as follows. In the evolutions that were done by East and Pretorius, we saw that the evolution was essentially conservative. Conservative means that the final hairy black hole has essentially the same total mass and angular momentum as the initial Kerr black hole, but just redistributed. Now, not all in the horizon, but some of it in the cloud. So, in other words, there is no very substantial emission by gravitational waves or gravitational cooling in the process. Gravitational cooling means ejection of, in this case, Broca field. So then you can look at the space of hairy solutions and see what is the maximum hairiness that's compatible with this constraint. Because when you get to very hairy solutions, you typically find something non-Kerr-like, namely, the dimensionless spin of the solutions becomes larger than 1. And there is no corresponding Kerr solution. This is not strange at all. Any object, let me put this, I'll make it rotate at 1 cycle per second. If you analyze how much J over M squared of this is orders of magnitude above the Kerr limit. If you put the G's. So this is something very specific for compact objects. If you look at the sun, it violates the Kerr bound. Now, these hairy black holes are much more star-like because it's a horizon inside of a star. So most of them violate the Kerr bound. Only in the vicinity of Kerr, they actually obey this. So that explains why we have to stay very close to the Kerr line in order to have a hairy black hole that can match the Kerr parameters. So that's how we got to that limit.
Thank you for the wonderful talk. It's very interesting. And my question is about this change in the distribution, depending whether you are talking about the scalar or the Broca case. Because it's not only a change in the geometry of the distribution of the field, it's a change also in the topology. So in the scalar case, you have this torus, which you can think as in terms of a topological invariant, like the genus. It has genus 1. And in the Proca case, it's spherical. So do you have some concrete results already or some insights about this relation between different spins of the field and different topologies? Like, for instance, in analogy with the Hawking spherical topology theorem for the event horizon, something like that. But in this case, for the surface of, I don't know, constant energy.
Thank you very much, Harold. So I would, of course, if you talk about surfaces of constant energy density, you could, to some extent, talk about topology. I prefer to talk about morphology because the space-time is topologically trivial if we are talking still about the solitons. Now, I would go one step backwards and ask about the simplest case, which is the static solution because the difference in morphology starts there. The fundamental state, the ground state, in the case of the scalar is something spherical, whereas in the case of the vector is something prolate. Why should that be? Let's start there. And then I can offer you a partial explanation. Because this is not something uncommon. We've seen this. This is a vector field. In a sense, it's a kind of a Maxwell field. Now, I always like to look at the simplest possible models from elementary physics. There is a very simple model, which is a soap bubble. I imagine a soap bubble. If it has no charge, it wants to be spherical. But if I give it a little bit of charge, I start increasing the charge, and there is something called the Rayleigh limit, and after which it becomes energetically favorable for the soap bubble to redistribute itself. You have a competition. You want to minimize the energy. To, deform the bubble costs energy. But to have all the charges together costs also energy. So what does it do? It kind of becomes prolate such that you can redistribute the charges in the poles. This is well known since the end of the 19th century. I'm not inventing anything. So there is a sort of vector-like effect there. So that is a step that made me feel a little bit comfortable about understanding something. Now, if I make this rotate in the vector case, I get this sort of structure, which is what would normally get if I think I could make something slowly rotate. I kind of now start, there's a sort of continuity between the static limit and now the rotating limit because it becomes spheroidal. Whereas in the other case, there isn't. And maybe that's why there is also a discontinuity in the dynamics. One case being stable and the other case not being stable. So this is the explanation I can offer you. I know it's not complete. And yeah, maybe there is something more insightful, but that's it. Sure.
Let's thank Carlos again.
Thank you very
It was
much.
a very nice talk.